Okay. Just a quick note that I got everything graded with respect to the last exam. I will open it up this weekend for you to go view and look at your answers. Do take a look at them. If you have any questions, feel free to bring them to class here, and we can go over them. See what else. There was a couple other things. No, I think I'll send an email on a couple of other things. Okay, so let us continue with where we left off, and we're almost done with this chapter. Shouldn't take too much more as far as classes. We've been talking about, excuse me, types of chemical reactions, and we have previously talked about the single replacement reaction. We were 6 of them. So we're going into single replacement reaction. We talked about that, about using the activity series from the single replacement reaction to determine whether a reaction will proceed as written. Okay, and we looked at first, just compared the metals and find out which metal is most reactive. Once we determine which metal was the most reactive, then you ask the question, is the most reactive metal already in a chemical form or in a salt form? And if the answer is yes, then the reaction will not proceed, and you write an R for no reaction. If it's not, you simply replace the metals, create the new ionic compound, balance it, put the states of matter on it, and you're good to go. Okay. Now, one thing to note, that if a reaction as written says no reaction, that means the opposite reaction will proceed. Okay. All right. So we went through that, and then we started to talk about the second type. Well, another example here of single replacement reaction. We looked at zinc nitrate. We're starting to look at zinc nitrate. It's an aqueous solution. And then we added sodium metal to it. And so the first question is the most reactive, which is the most reactive metal? And we use the activity series, which you find on the periodic table. Okay, and we can see here that sodium is in that position and zinc is in this position, which tells you that sodium is much more reactive than zinc. And then the second question would be to ask, once you determine which is the most reactive, in this case, sodium is most reactive, is sodium in an compound form? Is it in an ionic form? And the answer is no, because it's an elemental form. Therefore, we then exchange the metals, okay, where sodium will replace the zinc in the zinc nitrate, and zinc will become zinc elemental zinc. Okay, and so we write that in this manner. Now, notice here that before we do anything, is since we know that sodium is going to replace the zinc, and we can see from zinc nitrate that there's 2 of them, there's 2 nitrate groups. We go to the periodic table on the polyatomic ions, and we look up the nitrates, and we find them to have a -1 charge. That's why there's 2 of them in zinc nitrate. We also know that zinc has a +2. That is why we have 2 nitrates. But we know when sodium becomes ionic, it becomes sodium plus. And so before we put them together, we write the ion sodium plus and the nitrate, NO3 -1. That being the case, then we know that we can simply put them 1 to 1. Okay, 1 nitrate per 1 sodium. And then we also know, because the reaction will proceed, is that zinc went from a +2 state to a 0 state. Okay, and that's a specific type of reaction. I'll have more to say here in a second, in a little bit. Notice where sodium went. Sodium element. What is the the oxidation state of sodium, the element sodium? Who can tell me that? What is the oxidation state of sodium element?
Is it table salt?
No, look at sodium. It's the element. What is the oxidation state of all elements? What charge would it have?
+1.
Nah, think about it again now. This is the element. How many protons does sodium have? So the element sodium. Okay, it's number 11 on the periodic table. How many protons does it have?
11.
11. How many electrons does it have? How many electrons does it have? It's number 11. It's got how many protons? 11. How many electrons? 11. Yeah. So the elements have an oxidation state of 0. There's no charge. Remember that. We talked about that a while back because they have an equal number of positives and an equal number of negatives. The positive being the protons, the negative being the electrons. Now we know that once it becomes an ion, that it will lose 1 electron and becomes +1. So the oxidation state of sodium nitrate is a +1. Okay? So this sodium that I'm circling is a +1. It's the ion. So it went from a 0 to a +1 in this reaction. In order to do that, it must lose an electron. Okay? Now, what's the oxidation state of zinc in this state when it's zinc nitrate? I just mentioned that.
0.
No, zinc nitrate. What is the oxidation state of zinc in zinc nitrate? What is each nitrate charge is? What is the charge for each NO3 group? -1. How many do we have? We have 2 nitrates. Okay? See 2 nitrates? There's 2 of them within the parentheses. Each one of those is a -1. Therefore, there's a total of a -2. Okay? That means as zinc nitrate, zinc must be a +2. Right? Because remember, when we put them together to write the formulas, we got to add enough positive and enough negatives to cancel each other out. All right? Plus, zinc is one of the 16. Remember the 16 I talked about? Group 1, group 2, and those 4 elements that have a constant oxidation number. So zinc always has a +2. All right. Now, what is the oxidation state of elemental zinc now? What I just circled. What is its oxidation state? You can tell me that. You can tell me what is the oxidation state of zinc let me change the color to make sure we are talking about the correct zinc, okay? I've put this in this zinc that I put in the circle, the yellow circle. What is its oxidation state right there as it stands? I heard a number. Okay, let me clear this up. This is important. Okay, we have to grasp this. Otherwise, we're going to have a little bit of a problem in the next chapter. Okay, we aren't understanding. All right, so let's make it so we understand what's going on here. Okay. All right. Let's take the first one, zinc nitrate. Okay. Zinc nitrate. Now, does everybody agree that the nitrate, the NO3 in parentheses, has a negative 3 charge. Excuse me, -1 charge. Okay. Where's it at? Right here on the periodic table. NO3 -1. Okay. That's called the nitrate, hence the name zinc nitrate. Now, going back to the table, so how many nitrates do we have in parentheses?
2 of them.
Got 2 of them, exactly. So we have a total of how many negatives?
2.
-2. What does that infer that zinc must be? We all agree that zinc is a metal. It's going to lose electrons and it's going to be a positive charge. But what is the charge of zinc in that state as zinc nitrate?
It'll be a +2 because it needs to equal the negative.
You got it. Okay. And so the zinc in this state has to be a +2. Okay. And the nitrates, because there's 2 of them, we got 2 of them, each one is a -1. Okay. Because remember, we need to put these all together to equal 0. Hence, that's the formula for zinc nitrate. Okay. Now, once this reaction proceeds, now look at the oxidation state of zinc in this state. Is zinc in this state, what I circled in yellow, is it bonded to anything?
No. So it'll
Not
have
at
a
all.
charge.
It has no charge. It's the element. And so here, it went from a +2 state to a 0 state. Why? Because it now it gained 2 electrons. Okay? It gained 2 electrons in this reaction. Now, let's take a look at sodium. Let me change the color here so I'll make sure we don't confuse it. Take a look at sodium. Oh, wrong one. No. Take a look at sodium. I'm going to make sodium blue here. Okay? Now, in that state, as it stands, what is the oxidation number of sodium? Is there anything bonded to sodium as is written there, what I circled in blue?
No.
No, it's the element. So what
So-
must be his oxidation state?
0.
Got it. And so here it starts off at 0.
So I have a
Okay.
quick question. So when an element is by itself, it is not going to have a charge, but if it's in a compound, it will. Correct?
Yes, correct. So it will not have what we call oxidation number. I've been using the term charge, but we're going to learn that get into covalent compounds because they have partial charge. The term oxidation number is more descriptive than the charge. Covalent compounds don't have a charge, especially when we put them in solution. They don't dissociate, okay? So the oxidation number of sodium right now as an element, as if all, just like the other 118 elements, is 0. Why? Because there's equal number of protons and equal number of electrons. Equal number of positives, equal number of negatives, resulting in the net oxidation number of 0, okay? Now, what about in the state of sodium nitrate? Sodium nitrate. What is the oxidation number of that sodium when it is bonded to the nitrate?
It should be a -1, right?
Mm-mm.
Oh, wait. No. It should be +1.
Yes, okay. Metals would never be a negative number. Why? Because a negative number infers that they gain electrons. And what I stated before with respect to metals, that all metals, at least at Chem 130, lose electrons. And when you lose negativity, negativity meaning electrons, you have a positive charge, a net positive oxidation number. So under this state, this sodium now went from a 0 to a +1 state. Okay, you see how this is working? And so zinc nitrate, okay, starts off as a +2 charge because it's a compound, and it goes to a 0 oxidation state. Sodium starts off with a 0 oxidation state and goes to a positive. So it lost the electrons. And when we balance this, we'll see that we're going to balance it with 2 sodiums. That means that each sodium gave up 2 electrons to give to the zinc to get rid of its +2 charge to become a 0 or an element. Okay, this is a type of reaction that we call oxidation reaction and reduction reaction. We're going to have more on that, but this is an introduction to that. So let me clear the table here. And so zinc nitrate in the presence of sodium does react because the sodium metal is more reactive based on the activity table, activity series. And sodium is not in a compound state, it is not in any ionic state, and therefore the reaction proceeds. Okay. Now we write the physical property. We had a question mark on physical property right here. We got a question mark in parentheses. And the question is, well, what do we know? Is this going to be a solid, liquid, or gas? Okay. And that sends you to the solubility rules. And so, you know, even that periodic table, again, I can't overemphasize it. And this brings me to a point here that anytime you see the cation to be part of the big 4, okay, I can't overemphasize this. And what do I mean by the big 4? I mean lithium, sodium, potassium, and ammonium. Regardless of what the anion is, it could be anything out there in the world, it will always be soluble, always. And one of the homework problems you saw, I believe, is potassium oxide, K2O. And many students are putting it as insoluble. Well, it's not, because potassium is one of the big 4. And regardless of who potassium is bonded with, it will always be soluble. Okay? And that's why we know that going back here to the equation, the sodium nitrate, we know to write it as an aqueous solution. Okay? And zinc now is the element. And we know that from the periodic table it gave you of which elements were solids, there's only 2 liquids and a handful of gases. Zinc is solid. So we know that would be S. We know sodium nitrate because we are starting with an aqueous solution, because zinc nitrate tells you AQ, we're in an aqueous solution. We're going to end up with a aqueous solution. Okay, so that is the physical states. And to balance this, if you follow the polyatomic ions, the NO3, you see we got 2 to begin with. All we got to do is stick a 2 in front of sodium nitrate, and that balances the sodium, the nitrates, which picks up the number of sodium. So we go back to sodium, put a 2 in front of sodium to balance the sodiums. Earlier I said that zinc is in the +2 state, and it goes to the 0 state by picking up 2 electrons. Well, that's how it picked up 2 electrons. It picked up 2 electrons because we needed 2 sodiums to get, because each one gives up 1 electron. How do we know that? Because sodium is in group 1. It has 1 valence electron. It's a metal. It's going to lose that 1 valence electron to give us a +1 charge. Okay? and we needed 2 of them. So following the electrons of who gains them and who loses them also helps you to balance out the equation. All right. Now, obviously, we don't write it with Na. You know, what does this infer? If we were to write it with Na, the Na2 nitrates, what does that infer about sodium? Okay. Who can tell me why would this be an incorrect formula for sodium nitrate based on what we talked about a few chapters back and we've been talking about throughout the time? Why would that be incorrect? Or is that correct? How do I know that this is the correct formula for sodium nitrate versus the other one with 2 nitrates? What tells me which one is correct? Anybody want to take a shot? So we think about it. I'll give you a hint. What group is sodium in?
Sodium's in group 1, so it's going to have a +1 charge.
Exactly. And
And
the
the,
night.
and the,
Go
and the
ahead.
nitrates, the nitrate has a -1 charge, and when it says there's 2 right there, that makes it a -2, so they're not balanced out.
Right. That infers that sodium would be a +2, correct? Well,
Yeah.
it can't be because sodium is in group 1. It only has 1 valence electrons to give up. So that formula, Na parentheses NO3 2, would be totally incorrect. Just simply because we know where sodium sits on the periodic table. Okay. Because one would be tempted to write it that way because it starts off with zinc nitrate. Well, zinc nitrate, we know, always has a +2, so we require 2 negatives from the nitrates to balance out the +2 of zinc. That's not the case for sodium. Okay. See how everything, hopefully, everything we talked about is slowly coming together. We went way back and we talked about the elements and what group they're in as far as metals. We talked about the electron configuration about them, the valence electrons. I stated all reactions, all the action occurs on the valence electrons. It either is going to lose an electron to get the octet, or it's going to gain electrons to get the octet if it's a nonmetal. Okay, so it's all about the movement of these electrons, either we're losing them and gaining them, and knowing where they're at on the periodic table to determine how many electrons they either lose or they gain. Okay. All right. So let us continue. All right. So that's basically what we're saying here about the nitrates. We might be tempted to write it as Na parentheses 2 because it's zinc nitrate started that way, but don't do that. Base your information on what we learned about the metals and where they at with respect to the periodic table and how many electrons they lose. Okay, here we have this reaction here. We have, if I needed to name SRBr2, okay, what name could I give that? Here, I circled it with the blue. What name could I give that? Because here's the reaction.
You want the actual name of what you circled?
Yeah.
That would be strontium bromide, right?
That'd be correct. Okay. Now, why wouldn't it be strontium Roman numeral 2 bromide? Remember the Roman numerals we did? Okay. The name is correct, strontium bromide, but why wouldn't Roman numeral 2 bromide. Okay, remember the sweet 16? Those were the 6 elements, the 16 metals, I should say, that have a constant oxidation number when they become ions. Group 1 had +1, group 2 had a +2. This guy here, SR, is in group 2. It's number 18. Excuse me, 18. No, excuse me, 38. It's right underneath calcium. And so being in group 2, we wouldn't put iron 2 bromide because we know it has a constant oxidation number. Okay, so with that being said, we had strontium bromide reacting with aluminum. And now we have to determine, would this reaction proceed? So we use the activity series. We find aluminum down here in the activity series. I've circled in blue. Okay. And we got to find strontium. And where is it? Do we have it? Who's more reactive? There, circle.
Wouldn't the strontium be more active
That is
than
correct.
the aluminum? So there wouldn't be a reaction, right?
Exactly. So strontium is more reactive than aluminum. Okay. So after we determine which metal is more reactive, we don't care whether it's ionic or elemental, just which metal is more reactive, strontium or aluminum. This activity series says strontium is. Then you ask the second question, is the most reactive metal in ionic form? And it is. It's a compound. It's strontium bromide. Therefore, this reaction would not occur. Okay? There would be no reaction. But, you know, you could easily have been given the other direction and said, all right, what about aluminum bromide plus strontium? Okay. Would that reaction occur?
Yes.
It would. Okay. It would definitely occur because, again, same procedure. Strontium is still more reactive than aluminum, regardless of what state it is, ionic state or elemental. We're just looking at the metal. And then the second question is the most reactive metal in ionic form. In the reaction I wrote, no, it's not. It's in elemental form. Therefore, reaction proceeds. And so what happens is we know that aluminum will go from a +2 back to the elemental aluminum, okay, because we're exchanging the metals. And we know that strontium has a +2, and so it would need 2 bromides because we know that the bromides have a -1, right? We know that because the bromides are in group 7. Bromine's in group 7, and when it becomes ionic, it's going to gain 1 electron. So the ion of bromine will be bromide, which has a -1. Strontium is in group 2, has a +2, so I need 2 of them, okay? And now I put these in solution, and then the question is, all right, would SRBr2, would that be soluble or insoluble? Because I got to put the physical state here. What would I put in there? How could I determine what the physical state is of strontium bromide? What would I use? What tool do you have that helps you determine whether SRBr2, strontium bromide, is soluble or insoluble?
The
'Cause we're-
solubility rules?
Solubility rules, and what do you think what would its solubility be? Anybody know? Okay.
It would be soluble, right?
Yeah, it would be soluble, exactly. The solubility rules are important, okay? That helps you with these reactions. Let's go through them real quick, okay? Now, and I saw this in a lot of the beaker activity. Now, this column here, label in blue, this is the insoluble column, okay? And this is the soluble column, what I did in red. Okay. Now, normally, any carbonate, any chromate, any phosphate, that's number 6, 7, and 8, okay? Normally, anything it is bonded to, any cation it's bonded to, it is insoluble, with the exception of only 4. And I think people forgot that. If I have any of these 4 cations, lithium, sodium, potassium, ammonium bonded to carbonate, there's only 4 carbonates that are soluble. Everything else is insoluble. The same is true for the chromate ion and the phosphate ion. Okay? So yes, if you saw sodium carbonate, you go to the table, you'll see carbonate and you think it's insoluble. But you got to take it one more step. You got to remember, number 1 in the soluble column. If you're dealing with sodium carbonate, it is soluble. All the other carbonates, all the other than those 4 combinations, are insoluble. The same is true with the sulfide. Normally, all the sulfides are insoluble, except those 4, and if it's bonded to calcium, strontium, or barium. Okay, so there are only 7 examples of sulfate compounds that are soluble. All the other 10 zillion examples of sulfide compounds are insoluble in aqueous solutions. And ditto for hydroxide. Okay, hydroxide, all hydroxide compounds are insoluble except for 7 of them. All right, for 7 of them. And so whenever you see sodium, you see potassium or lithium or the ammonium as the ion up front, you can automatically say it is soluble. And so you gotta look at not only at the anion, then you gotta go back and check, okay, is it part of the 4 there, or the other 3 like strontium, barium, and calcium, where you will find those to be soluble. Okay, so that would help you in determining solubility, which in turn, I lost my slide, which in turn will help you with the physical state. Okay. All right. So the activity series for single replacement reactions. Okay. Now, excuse me. We have this reaction here. All right. So you might say, wait a minute, I don't have a metal here. We've been working with metals before, right? We got strontium and aluminum are using the activity series, but all of a sudden I got hydrochloric acid. Okay, well, remember on the periodic table with respect to the activity series, that scale is relative to hydrogen. And that's why you will find hydrogen right here in parentheses. Okay, and the elemental hydrogen will be H2. The ionic hydrogen could be in the form of a proton, or it could be in the form of water. Okay, so you proceed with the same scenario, asking the same question. In this case is we're comparing aluminum with hydrogen. And the question is, would this reaction proceed? Well, you go back to the activity series and you find aluminum down here in the bottom left corner and hydrogen way over here just past lead. So aluminum is a lot more reactive than H or hydrogen. And so what that tells you is the next question is the most reactive metal / hydrogen in ionic form. And the answer is no. Therefore, reaction proceeds. Okay? The reaction proceeds, and if you take hydrochloric acid in the presence of elemental aluminum, you get a reaction. And the product you generate is hydrogen gas. Okay? And then the corresponding, because you are displacing the aluminum with the hydrogen, are you not? Just like we did with the other metals. The aluminum now displaces the hydrogen in hydrochloric acid to give you aluminum chloride. And the hydrogen, which is in +1 form, goes back to elemental form because that's the ionic form of hydrogen. It's a proton, and it sends it back to elemental form, which is gas, hydrogen gas. And we know it's diatomic, okay? In fact, you will see by looking at the periodic table that hydrochloric acid will react with where H is, any metal behind it, hydrochloric acid will react with it. And above that, it's not going to react with copper or silver or mercury or gold. Okay, hydrochloric acid, those are very inert, which is a good thing for copper. A lot of we want copper pipes to be totally inert and not react with acidic water. Otherwise, you'll dissolve your copper pipes. And so we got aluminum chloride. If we look at the solubility rules for aluminum chloride, we'll find the chlorides to be soluble when it is connected or bonded with aluminum. Okay. And then H2, obviously we know it's a gas. It's one of the diatomic gases that we have. And then we need to balance the equation. Once we get the physical states, we got 3 chlorides from aluminum chloride. We can balance that out by putting we can put a 6 here, right? How do we come up with 6 hydrogens? What can we do? Let's go back to analyze that. What can I do? You just saw the answer, but how did they get to that answer with 6 HEl in front? What can I do?
Well, you have to balance the equation, right?
Yeah, that's what we're going to do. We balance the equation. We're going to break it down. Okay. -2. All right. Well, let's say we haven't seen the answer, but we got to balance it. And so generally when I see the aluminum and hydrogen, the elements, I leave those guys to last. And let's see what we can do by first placing, if I put a 3 in front of HCl, okay, doesn't that increase my chlorides? If I put a 3 right here, doesn't that balance my chlorides? Yeah. But then I have a problem here because now I got 3 hydrogens on the left and 2 on the right. So I got to find some way to balance that out. The hydrogens, I've got my chlorides balanced, my aluminums are balanced, my chlorides are balanced, but the problem child is my hydrogens. I got 3 hydrogens on the left and 2 on the right.
So then that means you have to find a common denominator, right?
Yeah, I could find a common denominator. I can boost up my hydrogens up to say 6 HCl's and put a 3 in front of. I can put a 3 here, right? And I could now make this over here to a 6. I can do that and cancel out that 3 written right there, cancel that out. Okay, so it gives me 6 hydrogens and 6 on both sides, but my chlorides went up to 6. So what can I do with that? How can I balance my chlorides now?
You multiply the AlCl 3 by 2, right?
That'll work. Let's try that. Let's put a 2 there. Okay, so that gives me 6 chlorides, which balances the chlorides that come from hydrochloric acid. My hydrogens are good at 6 on both sides. And now my aluminum chlorides went up to 2, so I get to balance that. So I put a 2 in front of aluminum. And do I look balanced here?
Dr. Fred, is
Yes.
that a 3 next to the H2 and the parentheses G?
No, that's a 3, yes.
Okay.
Yeah, that is a 3. I got too close there. Let me cancel that out. Move it out a little bit. I'll cancel it out with the red there. And I'll put that 3 a little bit further away. A little better? Yeah, that's a 3. Okay. And so now it looks like I'm balanced. I got 2 aluminums on the left side. I got 6 hydrochloric acids, okay, which gives me 6 hydrogens on the reactant side and 6 hydrogens on the product side because they got 3 molecules of hydrogen. I got 2 aluminum chlorides, which gives me 6 chlorides and 2 aluminums. And it looks like I'm balanced, which is consistent with that number. Okay. All right. Let me ask you a question. If I have 4 aluminums, let's just say I got 4 aluminums to begin with. I start off with aluminum, 4 aluminums. How many hydrochloric acids do I need for this reaction? What's my ratio there between aluminum and hydrochloric acid? It's 2 to
So
6.
it's saying for every 2 aluminums, there's 6 hydrochloric acids?
That's correct. So if I start off with 4, how many hydrochloric acids do I need?
You would need 12, right?
Got it. Okay. That ratio, that number we just used, we're going to set up, we're going to start setting them up with ratios. If I start off with 4 aluminums, okay, and I'm looking, the question is, I need to know how many HCl's I have. Well, from the balanced chemical equation, I know that there are 6 Cl's per 2 aluminums. That's my ratio. Okay, and that would give me how many HCl's I need, right? Because when I do the math there, guess what? My aluminums cancel, leaving me with units of HCl, which is what the question was asked for. Okay? Recall when we did the ratios and unit conversions, millimeters to inches or centimeters to inches, whatever units we needed, we had a ratio. You know, if I say to you, you know, you're traveling 50 miles per hour, that's a ratio that I can write as 50 in the numerator, or this is the same scenario. And that's why it's crucial that we need to balance the equations properly, because we're going to be getting into these type of calculations. Right now, using this, that means that we need 12 hydrochloric acids, right? I could have asked, what if I had 1,000 aluminums? Well, how many HCl's do we need? I will use the same ratio.
It would
1,000.
be like, it would be 3,000, wouldn't it?
Exactly. 1,000
Three.
times 6 divided by 2. That same ratio is still there. It will never change. It is the balanced chemical equation.
So I have a
Right.
question. When it comes to the ratios, you're saying the ratio right here is 2 to 6
Yes,
right now.
right now.
So you would want to use the lowest, like reduced ratio, right? Which would be 1 and 3.
Can I reduce anything? Can I reduce those coefficients any further?
Yeah, that would go down to 1/3, wouldn't it?
Yeah, but the coefficients are always whole numbers. Okay? So even though 2 and 6 are divisible by 2, 3 isn't. 3 is not divisible by 2 because you end up at 1.5. So you want your coefficients to remain the lowest common number that is without going into fractions.
Okay.
Okay? So it is 2, 6, 2, and 3.
Okay.
All right? All right. Just like the subscripts are always whole numbers, the coefficients will always be whole numbers. But if you did balanced it, okay, let's say you did balance the equation, but you ended up with, let's say, 4 of aluminums and 12 hydrochloric acids and 4, let's say you were doing the and you go one more, you're doing the balancing the equation, and you ended up with these coefficients, 4, 12, 4, and 6. Well, those guys are all divisible by 2. So in that scenario, yes, you would bring it down to the lowest common number, which in this case would be 2, 6, 2, and 3. Okay? Because it is possible when you're doing the balancing that you end up with higher numbers, and that's okay. Is get to the number you need to get things balanced. But once you get there, your last check is to see that if any number is divisible, if you can bring those numbers down to the lowest whole number. Okay? All right, let me clear this up. And that exercise we just did, that is the introduction to the subsequent chapters that we're going to be talking about when we start to calculate. Well, you might be given a scenario where you said, all right, I need 100 grams of hydrogen gas. Okay, well, how many grams of aluminum do I need? Could be a typical question. Okay, or if I start off with 50 grams of HCl, how many grams of aluminum do I need to get this reaction to proceed? And we're going to do some conversion the grams to what we call moles, because what the common factor is for these chemical reactions is the unit moles, M-O-L-E. We'll get to that with time. I can go from aluminum to hydrogen, but the only way to get from aluminum to hydrogen, I have to go through what we call moles. Okay. And so what this is telling me right now, that balanced chemical equation is telling me 2 moles of aluminum require 6 moles of hydrochloric acid. It also tells me that 2 moles of aluminum will make 2 moles of aluminum chloride and 3 moles of H2 gas. So right now, where I just said molecules, but I can take that word molecules out and insert it with the term moles. And moles is nothing more than a big, gigantic number, which will become clearer here pretty soon. All right. So for single replacement reactions, this basically flowchart just summarizes. Once you determine the most reactive metal, you ask the question, is the most reactive metal in salt form? If the answer is yes, you get no reaction. If the answer is no, then you have a reaction and you just simply substitute the metals, okay, for single replacement reactions. Now, for double replacement reactions, notice here we have AX, which again is an ionic compound. X could be a single anion, or it could be a polyatomic anion, okay? But you start off with AX and BY. In both cases, notice this physical state is aqueous. Both reactants are soluble, hence AQ. Now, once we mix them together, they're simply going to exchange partners. And so AX now exchanges partners with BY to become BY. Okay, let me color code these. And BY exchanges partners with X to become BX. Okay, simple exchange of cations and anions. If a reaction proceeds, that is denoted by whether any of these products are insoluble. In this general example, AY is insoluble, and we denote that by the symbol S. And that is that information comes from the solubility table. That's why I made reference to that earlier. If any of the products are insoluble, then we get a reaction. If both products that you create are soluble, no reaction. Okay, all they did was exchange partners. And a good example of this basically is you got two clear liquids, everything's in solution, and when you put them together, you form a precipitate, and you get a cloudy material. And if you let it sit there, you'll see the solid would settle down to the bottom of the container. That is a positive reaction. Okay.
I have a quick question about this. I checked out one of the Dr. Kim videos that showed like the whole list of the chemical reactions.
Mhm.
And for double replacement, it listed it as M1 plus X,
Okay.
plus M2 plus Y,
Yeah.
versus M1 plus Y plus M2 plus X.
Yes.
So this is the exact same thing. So A and B are literally just metal 1 and metal 2.
You got it. Two different metals. In fact, in that table, previous slides I had where I listed all the general formulas, all the 6 general types of reactions, you'll find that example of M1 and M2. Here, A and B are totally different metals, okay? If they were the same metal, then obviously they're not going to react with each other. It's going to stay in aqueous solution. So A and B are totally different metals. A could be sodium, B could be potassium, okay, or some other silver, or some other metal, okay? All right. And the thing to take away from this is simply the anions and the cations exchange partners. And by exchanging partners, they created a whole new compound. Now, if they're in aqueous solutions, and the solubility rules then define whether a reaction proceeds or not. Okay. We also call that a precipitation reaction because that's what that solid material is. The insoluble material, it precipitates. Okay. Solid forms, the reaction occurs. No solid forms, which is again governed by the solubility rules. No solid, and all the products are soluble. There's no reaction. Okay. So we got to learn the solubility rules, and I went over these a bit, but here we go again. The right column is the insoluble. I emphasize number 6, 7, and 8. Normally, everything that is bonded to those anions are insoluble, except that they're bonded to the 4 of lithium, sodium, potassium, and ammonia. And number 9, everything is insoluble unless they're bonded to the 7 examples I stated. And the same is true for hydroxide. Everything is insoluble unless it's bonded to the 4 in number 1, coupled with calcium, strontium, and barium. Okay. With respect to the soluble, whatever is bonded to those 4, regardless of what the anion is, could be anything. It is soluble. Okay. A lot of our medications are bonded with these 4 simply because of their solubility, and they're easy to digest and they're easy to go into solution. They put them into the salt form to get them for us to get them in solution for us to absorb them a little bit better. Number 2, again, acetate, regardless of what the cation is, okay, it is soluble, the same as nitrate. Regardless of what cation you're using, it is soluble. The halides normally are always soluble. The chlorides, the bromides, the iodides, always soluble, except these 3, okay, which are heavy metals: silver, mercury, and lead. Those guys bonded to the halides are insoluble and have a precipitate. In fact, that's how we test for chlorides in water and bromides and halides. We react them with silver nitrate, for example, which is soluble. And if there's any halides in your water, it will precipitate and the solution gets a little cloudy. All right. With respect to the sulfates, also, just like the halides, all soluble except when it's bonded to calcium, strontium, barium, silver, or lead. Those five sulfates are insoluble. Okay. Those 5 sulfates. So that's how we use the solubility rules. Okay. And you got to do a second check, even though you're dealing with the carbonate. Yes, you can say automatically it's insoluble unless it's one of the 4 up here: lithium, sodium, ammonium, and potassium. Okay. So you got to take it just one more step to verify that it's not those 4. So let us go through a couple examples. All right. So we have here barium nitrate and magnesium sulfate. Okay. So we have 2 soluble salts, 2 different metals, barium and magnesium. One's a nitrate, one's a sulfate. All right. So basically we exchange the partners and we end up with barium sulfate and magnesium nitrate. Well, we need to check the solubility and verify that, yes, barium sulfate is insoluble. Well, the solubility rules down at the bottom normally tell us that all sulfates are soluble except, guess what? Barium sulfate with the square box there. That is insoluble. Hence, we put a solid there. Okay. And then we know that magnesium, we checked magnesium to verify that, yes, it's soluble. We go down to the nitrates and we see the nitrates that regardless of what the nitrates are bonded with, any metal that is bonded with any cation, it is soluble. Therefore, we have the AQ. Okay. Now, my suggestion first is to break these guys into ions. So to make sure you got the correct ion set up before you I went ahead and gave you the products, but before you do that, break them down into the ions. Okay, we know that barium is in group 2. Everybody agree on that? Okay, so it's got a +2 charge. And the nitrates, we got 2 of them, okay? But we know that from the polyatomic ion table that every nitrate has a -1 charge, okay? And I put a 2 up front so I keep track, because to balance these, my suggestion is follow the polyatomic ions. Okay, magnesium is in group 2. So break it down to the ions. Now, why do I want to do this? Because I want to make sure that I put them together as products. And SO4, based on the polyatomic ion, is a -2. Okay. Now go over to the products that I'm going to create. And what I'm doing is I'm going to have barium. I'm exchanging the partners. So I got to put together barium, which has a +2. And I'm going to add that to the sulfate. Okay, so I don't put them together just yet. Just put them together just with respect to ions. And then put my plus there. And then I'm exchanging the magnesium with the nitrates. I know that Mg has a +2, okay? And I'm going to exchange that with the nitrates. And so that's NO3 -1, okay? So I broke everything down to ions to make sure that I put everything together. All right, so I go back and I look at my barium sulfate. Barium has a +2. The sulfates have a -2. I can easily put those together as a 1-to-1. Everybody see that? Okay. I look at magnesium. Magnesium has a +2 also, but the nitrates have a -1. That means I need 2 of them. I need 2 nitrates to put them together. Okay, now I can write the formula, and hence I can write Mg parentheses, because I need 2 nitrates, parentheses subscript 2. Okay. Everybody see why I do that? So I can put the products, the new products, back together again with the new partners in the correct ratio. Okay. Now, once I've done that, I went and checked the solubility of each of my products. We just went through barium sulfate, realized that barium sulfate is insoluble, so I put a solid, which means a reaction proceeded. And magnesium nitrate is soluble, therefore it's AQ. But the fact that we got one solid tells us reaction proceeds as written. Now I gotta balance everything. Here, it looks like everything just by default balanced out. I got 2 nitrates in the form of barium nitrate, and I got 2 nitrates in the form of magnesium nitrate. So the nitrates are balanced. I got 1 magnesium as reactant and 1 as product. Magnesiums are balanced. The barium, 1 barium as reactant and 1 barium as product. So just by default, because the charges of the cations, they are balanced. Okay. So the reaction just balances out all by itself. If I have 1,000 million molecules of barium nitrate, how many molecules of magnesium nitrate do I need? Let me restate that. If I have 1 gigaplex molecules of barium nitrate, how many magnesium sulfates do I need? All right, well, maybe that number's too big. How about this one? If I have 1 barium nitrate molecule, how many magnesium sulfate molecules do I need? What's the coefficient in front of magnesium sulfate?
Four.
Oh, no, no, no.
What?
What's the coefficient in front of magnesium sulfate?
There's none, or it's just one.
Exactly, it's 1. What's the coefficient in front of barium nitrate?
One.
1, there you go. Because remember, just like in algebra, if there's no number in front of it, it's assumed to be 1. It's taken as 1. And so now let me ask you the question. If I have 1 billion molecules of barium nitrate, how many molecules of magnesium sulfate would I need?
1 billion?
1 billion. How many molecules of barium sulfate would I make? 1 billion. What's the ratio? 1 to 1. There's a 1 in all of them. So if I have 1 billion molecules of barium nitrate, I need 1 billion molecules of magnesium sulfate, which would give me 1 billion molecules of barium sulfate, which would give me 1 billion molecules of magnesium nitrate. Okay? And the coefficient right there, everybody's 1 to 1. So that's pretty straightforward with respect to how many molecules I need. And so if I need if I say 1 googolplex, which is supposed to be a real number, who knows? You know, of barium nitrate, I need one googolplex of magnesium sulfate because of that ratio. Remember, once we balance these equations, that ratio, whether we do it in the lab in small scale or whether we do it in large scale industrial plant, that is the same ratio that we will have. Okay. All right. So let's do one more and then we'll probably call it. All right. So here what they're telling you here is to balance these type of reactions, follow the polyatomic ions. And by default, the chemical reaction will balance itself. Okay. All right. Let me clear this up. All right. So the question here says, all right, we got lead nitrate. Okay. Aqueous, meaning it is soluble. And we have potassium iodide. Okay. And aqueous, meaning that potassium iodide is soluble. How do we know that? Well, hey, just to verify, look at the nitrates. What do we learn about the nitrates? The nitrates, regardless of what the cation is, whatever the metal is soluble. The iodides, which is part of number 4, are always soluble, especially if they're bonded with the guys in number 1, potassium. So they're soluble. So it's correct. Yeah, they're both aqueous. Okay. Now we exchange the partners. So the lead, reacts with the iodide. Okay. But before we do that, break it down to the ions because you want to make sure you are putting them together in the right ratios. So what is the oxidation number of lead in this state with lead nitrate? What must it be?
One.
Okay. What is nitrate? NO3. Remember what the oxidation? It's a
3,
negative.
right? But there's 2 of them, it says.
Got it. There's 2 of
Okay.
them. Each one's -1. So that means that lead has to be +2. Okay. And then we got 2 nitrates. Each one has a -1. Okay. And so then we go over here with the potassium. I'm just going to put it right there. The potassium, what is the charge on potassium?
Positive
+1.
1.
Exactly. And iodide would be -1. It's in group 1. So I broke them down into ions so I can make sure that I put them together properly as my products. Okay, so I draw my arrow. And what we're doing here, we're exchanging partners. So the lead now bonds with the iodide. and we're still using lead 2. Nothing's changed there. Okay, but we're going to bond it with iodide, which has a -1, but we need 2 of them, correct? Everybody see that? Okay, and then we're going to make the other partner, new partner, the new compound where we are taking potassium, which is a +1, and we're combining that with the nitrate, which is a -1. Okay, it's a -1 up there. I want to make sure I got all the charges on there. And so by breaking them up into the ions, we can be assured that we put them together properly. Okay. And that's our formula. Potassium nitrate. Okay. And then we figured out we needed 2 leads, 1 lead for every iodide. So we need 2 iodides. Let me clear that up so we can see that. Okay. And then, so those are the formulas of lead iodide and potassium nitrate. Now, how do we know that it's a solid as far as lead iodide? Well, we go to the solubility rules and we look for the halide, which is number 4. But anytime you see lead X, X represents either chloride, bromide, or iodide. It is insoluble. Hence, lead 2 iodide is a solid. Potassium nitrate, well, we know the nitrates are always soluble. And then coupled on top of that, it's tapped in and it's bonded with potassium. So it's obviously going to be soluble, both of them. Okay. Follow the nitrates. We started off with 2 nitrates here. So we're going to need 2 to balance the nitrates. Oh, yeah, okay. Sorry, I got carried away with the time here. But yeah, I went over time. And so we got to balance, follow the nitrates, that balances out, and it comes out. We needed 2 potassium nitrates, which then we're going to kick in 2 potassium iodides to balance the iodides. Okay? And the potassium. So the ratio is 1 to 2 with respect to lead nitrate and potassium iodide. All right, so let me stop it here. I was hoping to get done with this, but no, that's okay. Better spend a little extra time and make sure we understand what's going on here. Any questions?